All right. So far, we have created a great foundation by understanding dimensionless numbers and the physical interpretation of mass, heat, and momentum transfer. These concepts aren't just theoretical, they form the backbone of how we model and analyze real world systems in chemical engineering. By now, we have seen how different types of transports are governed by similar mechanisms. They are all driven by gradients and resisted by diffusivities, whether it's velocity, temperature, or concentration. Now, with that foundation laid, we are ready to enter into one of the most exciting and unifying parts of transport phenomena, transport analogies. These analogies allow us to predict heat or mass transfer behavior from one momentum to another, especially useful in scenarios where obtaining heat or mass transfer data directly would be complicated or time consuming. So, up next, we will take you through the general relation behind these analogies, understanding what assumption they rely on, and explore the most widely used term like Reynolds, Chilton-Colburn, and Prandtl's analogy. Let's dive into this. Firstly, we're going to look into the friction factor. From the previous segment, you have learned about the physical interpretation of physical friction factor. Now we are going to continue this. We got the equation half rho V infinity F is equal to mu by delta, which we learned from the physical interpretation in the previous segment. On multiplying LCH both the term and rearranging the term, we get half F RE is equal to LCH by delta, where LCH is equal to the characteristic length, F is the friction factor, RE is the Reynolds number, and delta is the momentum transfer boundary length. We got H is equal to K by delta T. Now moving on with the heat transfer coefficient. Again, we know that QW is equal to minus K del T by del Y at Y is equal to 0. This is the Fourier's law of heat conduction. And QW is equal to H into TW minus T infinity, which is the Newton's law of cooling. On rearranging the term and bringing del T by del Y at Y is equal to 0, which is the interface thing, we get the equation H is equal to K by delta T. H stands for heat transfer coefficient, and while K stands for transfer coefficient. Del T is the thickness of the heat transfer. From the dimensionless number, we got the idea that Nusselt number is equal to H into LCH by K. On equating H is equal to K by delta T and Nusselt number is equal to K LCH by K, we get the equation LCH is equal to Nusselt number into delta T. Now moving on to the last segment, that is the physical interpretation of mass transfer coefficient. From last segment again, we got the idea that Kc is equal to minus dAb upon CaW minus Ca infinity into dCa by dy at y is equal to 0. Again, rearranging the term and bringing del Ca by del y and in LHS, we get the term Kc is equal to dAb by del C. Again, from dimensionless number, we got the idea that Sherwood number is equal to Kc into LCH by dAb. This number can also be called as Nusselt number in mass transfer. So finally equating Kc is equal to dAb upon del C and Sherwood number is equal to Kc into LCH by dAb, we get the idea that LCH is equal to Sherwood number into del C, where del C stands for mass transfer boundary layer thickness. So from the friction factor, we got LCH is equal to half F RE into del. From heat transfer, we got LCH is equal to Nusselt number into del T. From mass transfer, we got LCH is equal to Sherwood number into del C. On equating all three equations, we get LCH is equal to half F RE into delta is equal to Nusselt number into del T is equal to Sherwood number into del C, which we marked as equation number 4a. On rearranging this equation and dividing it by Reynolds number on all three sides, we get half F delta is equal to Nusselt number upon Re into del T is equal to Sherwood number upon Re into del C, where Nusselt number upon Re is equal to STH into PR, where STH stands for standard number of heat, while SH upon RE is equal to STM into SC, where STM stands for standard number of mass, while SH stands for Sherwood number, RE stands for Reynolds, and SC is the Schmidt number. Hence, we can rearrange this term for 4b as half F delta is equal to Nusselt number upon RE into del T is equal to Sherwood number upon RE into del C. Combining all equation and our newly generated equation, that is Nusselt number upon RE is equal to STH into PR and SH upon RE is equal to STM into SC, we get. So we can again regeneralize our equation before, that is half F delta is equal to STH into PR into del T is equal to STM into Schmidt into del C. Hence, 4CA is our generalized form. That is half F delta is equal to STH into PR into delta T is equal to STM into del C into Schmidt number. This generalized equation will be further used for our Reynolds analogy, for our Chilton-Colburn analogy, and our PRANDTL's analogy. Now let's move on with our first thing, that is Reynolds analogy. From the generalized form of transport analogy, we got the term half F del is equal to STH into PR into del T is equal to STM into Schmidt number into del C, where STH stands for standard number of heat transfer and STM stands for standard number of mass transfer. Please do remember that Reynolds analogy is only and only valid for the gases, and no other condition it is valid for. In Reynolds analogy, we do the first assumption, that is del is equal to del T is equal to del C. And our second analogy stands for, with the first analogy, we get the idea that F by 2 is equal to STH into PR is equal to STM into SC. We take the second analogy, that is Prandtl number is equal to Schmidt number is equal to 1. So putting this value of A2 into equation number 2, we get F by 2 is equal to STH is equal to STM, which we define it as equation number 3. On moving on, so as I said before, equation 3 is F by 2 is equal to STH is equal to STM, which is known as the Reynolds analogy. And this is only and only valid for gases. We also have an equation, that is T is equal to TW plus T infinity by 2, which is the average temperature. And every time we take the average temperature. With this, I would like to conclude the Reynolds analogy and move on with the Chilton-Colburn analogy.
Now we will move forward with Chilton-Colburn analogy. So we have seen the Reynolds analogy. Reynolds analogy is valid for only gases. We can't apply Reynolds analogy for liquids. So now we move forward and we will use Chilton-Colburn analogy. This is valid for gases and liquids for both of them. And it also having some limitations which we learn later on. But now on, we move forward. As we have seen, a generalized form of transport analogy, which is half F delta is equals to standard number for heat transfer into Prandtl number into delta T equals to standard number for mass transfer into Schmidt number into delta C. Here, then we will divide the delta by delta T and we will write it as a Prandtl number of power 1 by 3. And also delta by delta C is equals to Schmidt number power 1 by 3. And then we get F by 2 is equals to standard number for heat transfer into Prandtl number power 2 by 3 is equals to JH. So from where we get this? So see, we have this general transport analogy, then then del by delta T, we can write it as Prandtl number power 1 by 3. Then we have substituted this value in this transport analogy and we get F by 2 is equals to standard number for heat transfer into Prandtl number power 2 by 3, which is equivalent to J of H. Now, Similarly, as we have done it for Prandtl number for heat transfer, now we will do similarly for mass transfer. Similarly, we will substitute the del by del C equals to Schmidt number power 1 by 3 in our generalized form of transport analogy, and we will get F by 2 is equals to Stanton number for mass transfer into Schmidt number power 2 by 3, which is equals to Jm. Here, Jh and Jm are Coulomb J factors for heat and mass transfers. Further, moving on, what are the limitations? So, like we have seen some limitations in Reynolds number. Similarly, in Chilton-Coleman also there are some limitations. Like the temperature we are using is equals to this is the average temperature is equals to TW plus T infinity by 2. Here T infinity is your bulk temperature and TW is the temperature at your interface. Further on, moving to the limitations, there is a range of Prandtl number. If Prandtl number varies from zero point 0.6 to 60, then only we can use the Chilton-Coleman analogy. So before moving forward in any questions, let's see firstly find the value of Prandtl number. If it lies between 60 to zero point 0.6, then use the Chilton-Coleman analogy. And also, the Schmidt number should belongs from zero point 0.6 to 3000. If your any question which having the Schmidt numbers range between zero point 0.6 to 3000 and Prandtl numbers zero point 0.6 to 60, then only use Chilton-Coleman analogy. Else, and also there is some a discrepancy. If your Prandtl number is near at the boundary of like it's near it like 0.625 or it is at 59.75, like the value of your Prandtl number, if it is near your boundary, so the error will be greater. The approximation, the answer will be not that much accurate. The error will be much. If your Prandtl number's value, for example, Prandtl number value will lie between the zero point 0.6 and 60, like 30 and like 10 or like 20, then the error will be less. But at the boundary of your limits, the error will be more. So keep remember at boundary, if you are finding any answers for Prandtl number using and for by using Schmidt number, then error will be more. Then moving forward, so there are some geometric limitations of so flow geometry. So there are some geometric limitations. For flow over a flat plate, we can use F by 2 is equals to JH equals to JM. For flow over a cylinder, we can use JH equals to JM. For flow over a sphere, JH equals to JM if Nusselt number is greater than 2 and if Sherwood number is much greater than 2. Flow in pipe, we can write it as F by 2 is equals to JH equals to JM if Reynolds number is greater than 10,000 for a smooth pipe. So now question is why? Why there is such discrepancy? Why we have not written the Chilton-Coleman analogy as F by 2 equals to GH equals to GM for each and every geometry? Why we are not writing this? So the reason behind it is like the exposed area. Like for flat plate, the exposed area is the surface, is the interface which you are using. So for that, you can write F by 2 equals to JH equals to JM. But for cylinder, the exposed area for cylinder may vary, may different. So that exposed area will create the difference. That's the reason you are not using F by 2 here. That's why you can't use F by 2 is equals to JH equals to JM. Got it? So that's the reason the Chilton-Coleman analogy having some geometrical limitations. Then moving forward, flow over a sphere. For flow over a sphere, JH equals to JM if Nusselt number is much greater than 2 and Sherwood number is much greater than 2. And similarly, in pipe, there is some limitations. So mainly this limitations is just because of the exposed area which through which the fluid is flowing. Now moving forward, So there are some questions. So basically, this is the concept of Chilton-Coleman equation. Chilton-Coleman.
So Radha have given you a lot of information about Chilton-Coleman, and even I've given you a lot of information about Reynolds analogy. These were the two main analogy we have learned in transport phenomena. And now we are giving you another analogy, which is apart from our course, and it's maybe an advanced analogy. It's a part of advanced transport phenomena, part of an. So Radha have given you a lot of information upon Chilton-Colburn analogy, and even I have discussed a lot about Reynolds analogy. So now we're going to move on to the next part, which is not the part of our transport phenomena, but maybe the part of advanced transport phenomena, which is the Prandtl, Taylor, and von Karman analogy in transport phenomena. These are the two advanced analogies for momentum, heat, and mass transfer. So we have already covered the questions about what are transport analogy, what are their uses. So the only question which arises and which we focus now is Prandtl-Taylor's analogy and von Karman analogy. So moving on with this, the first analogy we're gonna see, the first analogy we're gonna see is the Prandtl-Taylor analogy. This analogy is developed by Prandtl and Taylor. This applies to turbulent boundary layer, and and in which assumes that eddy diffusivity of momentum is equivalent to heat. This analogy is best and perfect for Prandtl number equivalent to 1, that is air. Moving on, we had some assumption also, that is, the first assumption is turbulent flow over flat plate. Secondly, similar eddy transport mechanism are usually avoided. No pressure gradient is considered, and we consider only steady state flow. We don't have much information about Prandtl's Taylor analogy, so we're going to stick with some gist which we have covered from advanced books and BSL books. So we got the first equation as Q upon tau W is equal to rho Cp into Tw minus T infinity, where Q is the heat flux, tau W is the wall stress, shear stress, and Tw T infinity are nothing but wall and free stream temperatures. Moving on, we also have a slide knowing where to use this Prandtl theory. So first, as we discussed before, it can be used for turbulent flow. Secondly, for flat plate, and third for air or gases, in which Prandtl number is equivalent to 1. So for Prandtl number very greater than 1, it is not accurate, or pressure gradient is not equivalent. So it is avoided to use for Prandtl number greater than 1, and only stick with Prandtl number equivalent to 1. Moving on. So the last analogy which we cover and will be explained by Radha.
Sorry.
Go. Now for the next analogy, Radha is going to explain you von Karman analogy. One.
So our next analogy is von Karman analogy. So based on integrating boundary layer equations, connects momentum and energy transfer, considers velocity and temperature profiles. Okay, so in this analogy, we are just integrating the boundary layer equations. The whatever the boundary layer conditions we will get, we will put that boundary layer conditions in our generalized analogy, transport analogy, and we will integrate it. So it connects some energy and momentum transfer, basically basics, and also it will consider some velocity and temperature profiles. So St, which is a Stanton number, is equals to Cf by 2 into Prandtl number power minus 2 by 3. Stanton number is h by rho Cp mu. This is the Stanton number for heat transfer. And here Cf is equals to skin friction coefficient. Then moving forward, d theta by dx plus 2 delta into rho divided by rho u square into dou p by dou x equals to tau w by rho u square. used with energy equation for heat or mass transfer. As Yash have previously told about the analogy, which is Prandtl analogy, in which we can't use that analogy for pressure variations and for Prandtl number greater than 1. So in this, by using this analogy, we can use this analogy where also where pressure is varying. So in any situation, in any case, if pressure is varying, then use this equation, this analogy basically where to use complex boundary layer flows. Like your boundary layer flow is very complex. Like you can't find an appropriate analogy to derive the equations and to derive the some normal equations. So where you will use this analogy. Pressure gradients must be should be present. The accuracy of this analogy is great, requires more data and integration. Yeah, but this is all the good part of it, like complex part will get solved, then pressure gradient if present, then it will also solve it, and accuracy is also good. But the major disadvantage of this is like it will require more data and integration. Basically, you need to have some strong concepts and strong solving of mathematics. So now the Prandtl number versus von Karman. So, what is the basically difference in the both of these analogy? So, Taylor eddy diffusivity analogy, moderate complexity. In Prandtl Taylor, there is not much complexity in solving the mathematics, but in von Karman, there is a lot of complexity for solving the equations. Okay, then von Karman integral method, higher accuracy. Then Prandtl-Taylor, best for Prandtl number approximately 1 for flat plates. Von Karman work for pressure gradients, wide Prandtl number range. Summary. Both analogies extend Reynolds analogy. Prandtl-Taylor for quick estimate in airflows. Von Karman for precise complex flow analysis and helpful in designing heat exchanger reactors, etc.